Hi, good day everyone. This is Maths Intellectual tutorial sponsored by Mathematical Intelligence, and today we are going to be commencing a topic titled Integration Properly. Integration. Integration. Basically, in today's class, we are going to be looking at the theory of integration and many things that maybe might not be captured in probably a normal calculus class or a normal integration class in a normal school setting. So, but today we are just going to looking at some of the few things that integration is all about. But today's class is just what integration is all about. Okay, now let's assume that we have a graph. Let's say we have something like this. Let's say we have something like this. Let's say we have a function f where this is our y and this is our x axis. Are you there? So, and we are now asked to, let's say we are asked to find the area of this portion. We asked to find the area of this portion. What are we going to do? Hmm. This is a function and we asked to find the area of this portion. What are we going to do? How do we find the area of this portion? How do we go about it? So this is one of the three ways, or this is one of the avenue where our integration came to play. Okay, and some of these things happen when you have maybe a field or probably something that is not very accurate in shape. You see that this is a kind of a curve from this side to this side, and there's a lot of things going on here. You don't have something if you have maybe a plane shape, maybe like a triangle or whatsoever, you can easily find the area of that. For what if you have a field whereby you are trying to find the area or something like that, you are going to use what we call integration in that aspect. So what comes about my integration that I'm talking about here? All right, so there is something, or there's a man called Riemann, and is one of the person that proposed this or is one of the how will I put it, is one of his method that we are going to use today. It's called Riemann integral. There's something called Riemann integral. Riemann integral. Riemann integral. Now, for this problem, now Riemann integral is when you have the integral from a to b of what? F of x dx. This is just the general formula for Riemann integral, or an integration, or a how do you guys put it, or a definite integral. Right there now, a definite integral is majorly mostly written like this, where this is our function f and we are trying to find the area from a to b. Right there, where this is your a, this is your b. So what do you do? There is what we call, I'm going to be introducing some concepts quickly. There's something we call lower sum, lower the box sum, upper the box sum. There are things we call those things. So basically, when you want to find the area from here to here, which is where your concept of integration comes in, what you just do is just we divide these things into compartments, rectangular compartments. That is, we divide it into different rectangular compartments, and then we'll find the sum. I get it now. We'll find the sum of each rectangle. Can you see it now? We'll find the sum of each rectangle, something like that. I get it now. We'll find the sum of each rectangle, and when we find the sum of each rectangle, we'll be able to high possibility arrive at what? The area of the shape. Are you getting the logic now? Rectangle A, rectangle B, rectangle C, D, E, F. I get it now, like that, like that. We'll be able to arrive at the area of the shape. But that is not basically everything we are doing today. Yeah? But that is what leads to what we call a new concept, which I'm going to introduce. Some of these concepts have been used in rain analysis. For those who have studied it before, this concept and some of these concepts have been used in rain analysis, and that is why I'm going to introduce it in this video here. And I said that because of all this rectangle here, this rectangle is what leads to something called our, so what we call lower Riemann sum, or lower debug sum. Let me write it, LDS, lower debug sum, is the equation is literally written as summation what, I starting from 1 to n of f, sorry, of of mi delta xi, that is lower sum. For upper sum, upper debug sum, the formula is written as summation I starting from 1 to n of capital Mi delta xi. I get it now. So what is all this concept I'm introducing? Some of this concept will look new to you, especially if you have not done linear analysis where you talk about Riemann integral. Some of this concept might look new to you, so you have to sometimes, because of this is just a, I'm just picking some points out of that course. Some of this is one of the reason why you might have some few difficulties, but this is the reason why I'm picking some points out of this aspect of mathematics, which is really nice, is that that aspect of mathematics best explain what is going on when you are dealing with integral. I getting it now. All right, so what am I doing here? This is our Riemann integral, which is our normal integral, which is also the definite integral we talk about, and we are having a to b. This is f of x, and then this is dx. So we are looking for the what, from this point to this point, we are looking for the area of this place. The area of this shape from a to b is what is going on here. I get it now. So what is going on here is exactly what I drew here. I get it now. So when you have integral from a to b of f of x dx, this is a, this is b, this is your f. So the integral from this place to this place is the area that is covers. I get it now. The whole area here is your what? Your integral. I get it. So integral is basically talking about area. I get it now. So which is something new for some who are not uh, mathematics students. So now, why am I introducing lower debug sum and upper debug sum? Lower debug sum is the is talking about lower and upper debug sum. They are both approaches to tackle this problem, which is what led us to this formula. I get it now. I'm trying to show you what led us to this formula. Lower sum is just like, is dealing with the triangles. I get it now. Upper sum is also dealing with the triangles. I get it. I'm trying to explain in a less technical way. I get it now. So lower the box sum dealing with the rectangles here. Upper the box sum is dealing with rectangles here. Now, question: the problem we are trying to find is the area of this portion, and the area of this portion is given as this formula. I get it now, and this formula is gotten from some of this concept I'm now introducing. Are you getting the logic now? So now lower the box sum is the summation of all the rectangle under the curve. Are you getting now? Lower the box sum is the summation of all the rectangle under the curve. While upper the box sum is the summation of all the rectangle that is the total rectangle, or the total finite number of rectangles that cover the area. I did now. That is the total number of rectangles that covers the area. That is total number of finite rectangles that cover the area is called the upper the box sum. I get it now. So I'll show you some diagram quickly and you get more enlightenment. All right, so now we have lower the box sum and upper the box sum. Can you see it now? Now, if you look at this problem, what we are trying to do, I want to repeat myself, we are trying to find the area of this field here, and The area of this field here is this integral. I get it now, which is A equals to this. That is the area. But how did they come about this? This integral is our definite integral, which is the basic of integration, the general formula for integration, generally for definite integral. I get it now. And how did they come about this is what I'm trying to explain. I get it now. Now, I started with we want to solve this problem of finding the area of this kind of what? This kind of field. I get it now. And for me to find the area of this kind of field, for me to find the area of this problem here, what I need is this and this. So for me to find the area of this problem here, I need to divide this what? This shape here into compartments of rectangles. I get it now. Those components of rectangles is what leads to this lower sum and upper sum. So, and I now say that lower sum is the summation of what the rectangles beneath the curve, and upper sum is the summation of the rectangles that covers the whole area. I get it now, which is what I want to illustrate better in this diagram I have here. Look at it here, the upper the box sum areas of that covers whether area above the rectangle, or how will I put it, whether sum of rectangles, rather sum of rectangles that covers the whole area I'm looking for. What I'm talking about is upper the box sum, just saying that it is sum of rectangles, sum of all the rectangles that is in that segment of area you are trying to look for. I get now. Sum of rectangles that covers the area you are trying to look for. I get it now. What I'm trying to say, look at it here. This is the area I'm trying to look for. From this point downwards to this place is the area I am trying to look for, to this place and to this place. So what are the rectangles that cover this place? This rectangle covers, this one covers, this one covers, this one covers. I there now. Do you get it? Do you get the logic? So, but for that is for upper the box sum, but for lower the box sum is the sum of rectangles below the curve. That is sum of rectangles of the area I'm looking for, but those rectangles are below the curve. Hidden now. So that's the difference. So lower the box sum is these are the rectangles beneath the curve, and this is the compartment I am trying to solve. I get it now. I get it now. A to B. Can you see it now? So these are the compartment I'm trying to find the solution to. I get it now. So now look at this and look at this. This for lower now, this one is not low, this one is upper the box sum, because this one is upper, this one is lower. Do you get the logic now? So now this brings us to the point of what we are trying to do, which is the Riemann integral. And so from lower sum, I get it now, from lower sum we have summation of what, starting from 1 to n. That is the number of rectangle. If you have 1 2 3 4 5 6 rectangle, you have 1 to 6. If you have 7, you 1 to 7. If you have 8, 1 to 8. But yet these rectangles here don't best give us the whole full area, because there might still be some few spaces left somewhere when you are trying to draw a rectangle in that kind of segment. So what do? We divide this compartment, each compartment, to smaller rectangles. We divide this one to a smaller rectangle, we divide this one to a smaller rectangle, smaller rectangle, smaller rectangle, smaller rectangle, smaller rectangle, smaller rectangle, until we get to a point whereby the rectangles now that have been divided to infinite kind of rectangles, that is, you have divided to an infinite tiny number of rectangles, such that it now looks like the whole shape. Do you get the logic now? It will now look like the whole shape at the end of the day. Do you get the logic now? So, and that will now lead us to our lower Riemann integral. So we are now looking at lower Riemann integral now from our lower Riemann sum. Our lower Riemann sum says that you have summation I start from 1 to n of what? Of mi delta xi small mi. This is infimum. I don't want to dive into that because of our um, limited understanding of real analysis. So now, and this is a lower Riemann sum. I get some of the rectangles below the curve, but for upper Riemann, but for lower Riemann integral, it is to now become integral from a to b of what? F of x dx. I get it now. And this one here is the lower Riemann integral. I don't know. Lower Riemann integral is this. While upper Riemann integral is the integral from a to b of what? Upper of f of x dx. I get it now. This is upper Riemann integral. This is lower Riemann integral. And they are both gotten from our lower sum and upper sum. I get it now. Now, how did this one become this? That is what I was explaining here. This is what I'm explaining in this place here. That is, since when n is 5, we have 5 rectangle. When n is 10, we have 10 rectangle. When n is 20, we have 20 rectangle. When n is 100, we have 100 rectangle. The more the rectangle, the smaller the spaces you have. That is, the smaller the triangle. I get it now. The more the rectangle, the smaller the rectangle. I get it now. So when n is 1 million, you see that it will be very, 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 very tiny. I get it now. So it keeps going, keep going until you get to a point whereby it looks like almost to infinity, whereby the whole space now look like the shape of what you are trying to look for. I get it now. And that's why we now change this one now becomes an integral. That integral from a to b, because it has become an infinite kind of thing of the function dx. I get it now. While the upper Riemann sum is integral from a to b of the function dx, and which is same thing as, I don't want to introduce many things because I'm not doing really with Riemann. Maybe when I'm doing analysis class, I'll integrate a lot of things like your this one here is what your supremum of the. I don't want to put too much terms. This is supremum of the lower sum. This is the infimum of the upper sum. That's the definition for lower Riemann integral and upper Riemann integral. But because of those who are not they don't have the knowledge of reanalysis, I'll not dive into that. I get what I'm saying. So now I want to recap quickly. We have this problem. We are looking for the area, and the area is this. So how do we get this? And this is our definite integral, and this definite integral is literally the basis of our integration. So integration, what is integration, is the question I'm trying to ask you, and I'm trying to explain integration using area. And the area of this shape can only be gotten by dividing each this segment into rectangles. That is, I'll now find the area of each of the rectangle and sum it together. I get it now. And the only way I can find the area of the rectangles and sum it together is using this lower sum and upper sum. I get it now. A lower sum is this, upper sum is this. I get it now. And this is how it looks like in real term. When you are looking at it in normal logical term, this is how it looks like. I get it now. Where this is your lower sum and this is your upper sum, and I used to the upper sum covers everything, lower sum covers only the under the curve, only rectangle under the curve. I get it now. Now this one now brings us to our integral, and basically I'm trying to prove how I got this area to be this. I get it now. So this brought us to our integral, which is a lower Riemann integral and also an upper Riemann integral, where our lower Riemann integral is defined as this, upper Riemann integral is defined as this. But how did we get this? I told you how we got this from our lower sum. No, when n is 5, that means we have 5 rectangles here. When n is 10, we have 10 rectangles here. When n is 20, we have 20 rectangles here. I get it. I get it logic now. But as n increases, we get high tendency of getting an accurate answer for this area. I get it now, because if I divide this thing into two rectangles, I may have some spaces on top or some spaces somewhere, especially when the curve is a very bent curve. This one is still a little bit smooth. You have very bent curve. Are you getting the logic there? If I'm trying to draw a rectangle, are you getting now? So, but as the n increases, we have a higher chance of getting an accurate area. So as this thing n increases to more than maybe a million or so, then it becomes integral to make it easier. Are you getting down? This integral is now talking about the movement here. Are you getting down? So that's what leads to our lower Riemann integral basically, and what leads to our upper Riemann integral. And here, when your lower Riemann integral and your upper Riemann integral are equal to each other, that is when this one and this one are equal to each other, basically it now gives us our Riemann integral, which is our area integral from a to b of what, f of x dx. I get it down. So, and this is what leads to our simple area for that curve. So is the area of this curve is basically this, which is integration. So the idea of integral is trying to find the area of a certain field. That is the idea of integral. So anytime you're integrating, have the idea or the mind that we are trying to find the a kind of area of a certain compartment. I get it now. Maybe a to b can be 0 to infinity, it can be minus pi to pi, it can be anything. I get it now. So you are trying to, especially when you are dealing with definite integral, what you are trying to do is find the area within a certain compartment. And this is what I want you to take home today. You are trying, when you are dealing with integral is talking about finding the area within a certain field, and that is basically what integral is all about. So if anybody asks you what is integration, integration is the opposite of differentiation. Integration is anti-differentiation. Yes, all those things are correct. And integration is also trying to find the area within a certain field. Basically it's just one of the major definition or major concepts about integration. So, and this is what I want to take home today, and probably in our next video we'll look at more things about integration. So this is all for today. I'll see you in my next video, but don't forget to also subscribe and share to those who need them. So if you have background on your analysis, you have more understanding about this. If you don't, you have a little bit difficulty, but if you go through it, you get more understanding. That's why I'm trying to break it down to the least way I can explain. So I'll see you in the next video. Don't forget to subscribe and also share to those who need it. So bye bye.